equal sum grid partition 1 and 2. So the first problem, we are given a m cross n matrix grid of positive integers. Task is to determine if it is possible to make either one horizontal or one vertical cut on such grid such that each of the two resulting sections formed by the cut is non-empty. So the cut can't be something like this, right? This way. I'm sorry. It can't be something like this or like this or like this, this, right? Because this section can't be empty. This section can't be empty. This section, right? So the next validation is sum of both the sections, sum of all the elements in both sections should be equal. Return true if such partition exists, return false otherwise. So if we do it in a 1D array, then we can get and extend the idea to a 2D array. So if we have something like this, right? So at any point, I'm going to check the consider this point as the partition and consider this section and this section and make sure if the sum is equal or not. If it is, then we can return true. So we can use prefix sum, right, of some kind here. So 1, 3, 6, 10, 11, 15, 21, 29, 8, yeah, 29. So if I am going to divide this right at this point, then this will be the one section and this will be the other section. So the one section, the first one, will have a sum of 10 minus 0, right? So I can consider something like this, right? So if I'm considering 4 as the partition point, with 4 being in the first section, then I'm going to say 10 minus 0 is going to be the first section's sum, and the other section will be 29 minus 10, and that is going to be 8 plus 6, 14, 14 plus 5, 19. So 19 is going to be the sum. 29 minus 10 is 19. That's it. So we can just iterate and see which section is giving me the equal sum. I can't consider this. If I'm considering this to be the partition, then one element is already there. So this is also a valid partition, right? It's never going to be this is the other section and this is the empty section, right? So now if we extend this idea, right? If we extend this idea, then I want to find for a 2D array the same thing but in column and row fashion, because we have to determine the two different cuts are possible or not. So if this is the grid, then I can maintain a row sum and a column sum, right? So for row sum, what I'll do is I'll maintain a row sum of row sum will maintain the sum of the rows, right? So it will be of size grid dot size. This will be grid size, and this will be grid 0 size. So this is basically row size, and this will be column size. Sorry for the bad handwriting. So how will we find the row size? That's pretty much straightforward. I can just iterate this way and just keep adding the row sum, right? So for each iteration, I'll keep adding the sum, and then when I move to this next row, I'll add that sum to the row sum, right? Now comes the part where we have the column sum, right? So what I can do is I can iterate this way and do the exact same thing. But we can do something better. Instead of having two passes, what if I can just iterate in this manner, just a single pass from all the cells of the grid, and basically add it to the row of I and the column of I, right? Column of J, my bad. What will this do is it will give me the row sum for this particular one, for this particular one, for this particular one, for this particular one. It won't give me the consecutive prefix sum, right, for the row and the column, but it will give me the row sum for each particular row. For each particular individual rows, we'll have the contribution in this row and column, right? Now, if I want to find the prefix sum, then I can just use this row vector and just try to do the exact same thing, and that's what we are going to do. So let me write the steps down. Create a row array, create a column array. Let me write this as the first step. This is the second step. Third step will be iterate and add the grid of I and j to both the row and column at the respective positions. By respective positions, I mean I and j for row and column respectively, and then we can just iterate and maintain, iterate the row while maintaining prefix row sum, but just the prefix row sum is not going to help me. Why? Because if I have something like this, right, and if I have something like the row as 5 and 6 and the column as 3 and 7, right? Now if I iterate, suppose I am extending to a different better example, something like 3, 2, 4, it can be something like again 2, 6. Now if I want to maintain a row sum, right, that will give me 3, 5, 9, but if I'm saying that this is going to be the one sum for the one section, the other section, to calculate that I need to have the total sum so that I can just subtract this value, and that's going to be 9, 11, 11, 6, 6, 16, sorry, 17, 17 minus 9 is going to be the other section sum, right, and that's going to be 8. So 8 is this sum, this section sum, and 9 is this section sum. So I can, in the first pass itself, calculate the total sum of grid, and here calculate the other section sum. If it becomes equal, if both becomes equal, return true. Do the exact same thing, repeat step 4 with column sum. In the end, return false, right? So this is going to take one pass, so O of m cross n, and this is going to take O of m, O of n, and that's it. So m cross n is going to be the major time complexity. So let's start coding it up. Row sum, let me call it just row. This will be grid dot size. Let me get the this is column size, this row is going to be the row size, and similarly n and column is going to be the column sum array. We need to maintain a sum for total sum. I'm just going to iterate. Similarly, I'll be iterating this way. This will be j, this will be n, j. I'm going to add the sum every time I just get a grid of ij. Now I'm going to add grid of ij to row of I. Similarly, I'll maintain do the exact same thing for column of j. Now I have both row, column and sum, right? So what I can do is get the row sum, right? We need to maintain a prefix row sum. So let me take a prefix row sum starting with 0. If I'm at ith position, that means I'm saying that I till 0, from 0 to I is the first section, remaining is the other section, right? So I'm just going to iterate till this point, because the last section for the row last point doesn't make sense, because we are told that every section should be non-empty, both the sections should be non-empty. So I just get the row sum, prefix row sum plus equal to row of I. Now I'm going to check if the prefix row sum is equal to the other section sum, that is sum minus prefix row sum. If it is, then return true. Do the exact same thing with column, right? Column, 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 return false. Let's submit this, see if this works. It does. Let's submit this. Time complexity will be of m into n. I'm sorry, O of m into n plus O of m plus n, right? This will be the time complexity. Space complexity will be it will be O of m plus n, I guess. Yeah, n plus n, right? Let's move to the second part of this problem. Equal sum grid partition 2. We're given the exact same thing, just that now if the resulting sum of both the sections are not equal, then what we can do is we can take the one section which has a larger sum and discount at most one cell from that section, so that that one cell won't be contributing to the sum of that section. But this should also hold true, that the section or the cell that is discounted, that is removed from the section, is not going to change the fact that the rest of the section is disconnected, right? It should still be connected. By connected, we mean that from one cell I can reach any other cell in that section. So if this is the grid and we have few elements, few cells, then what we are saying is, let me just create the one section. Suppose this is the one section and this is the partition, right? So now if the sum is S1 and S2, which is S1 is greater than S2. Now I can do is I can see how much greater S1 is from S2. That is S1 minus S2 is a value that I want to be reduced from S1. How can I reduce it? I can reduce by removing that one element, and that one element should have a value S1 minus S2. Right? Suppose that S1 minus S2 value is a 6, then I can remove the 6 and see the fact that from any cell I can move to any other cell. Correct? Does that hold true with this 5? If I remove this, that still holds true. It still holds true. For this one, still good. For this one, it's still good. For this one, it's still good. But for this one, if I remove this, it is still it does still hold good, right? So what we see is this section holds good even if I remove any other element. But what if the section was this? Now does this hold good? The 2 that I removed is going to block 1 from being connected to 3. Similarly, 3 is not connected to 1. Uh, Now if I remove 3, then still 2 won't be connected to 4. But what if I remove 4? All of them are still connected. If I remove a 1, they are still connected. So we see that if there is a partition that causes just a single row or single column to be separated, then we can only choose the corner elements, and we can't choose 2 and 3. The elements between in between the corner elements can't be chosen, right? So we see that, and that still holds true for the other section as well. And vertically, if we see that, it still holds true. Right? So here I can remove this part and this part. Suppose the section was divided in this way. This can be removed, this can be removed, this cannot be removed, and this cannot be removed. So this is the problem, right? And we need to return true or false. Just the fact that if we can do it with or without removing the cell. If we can without removing the cell, well and good. If we can't, then we have to remove and see if we can or not. So if we can, we return true. If we can't, we return false. So we can take a similar approach where we try to find the row and column, and then the row sum and column sum in a prefix way. But every time we check that the sum of one section and is greater than the other section, then we try to find the lookup value, the difference value, right? This difference value should be present in the section which has a larger sum, right? Now if it is present, then we can return true. If it is not present, then we move to the next row value and see if that is going to work or not. Same thing needs to be done for the column value. But the fact that we need to maintain a grid, sorry, not a grid, but a set or a map to see what all values lies in the one section, and similarly what all values lies in the other section, right? So the thing is, what we can do is, it's difficult to explain here, but the one approach that we can do is maintain a set, right? A map is not required, but a set can be maintained for this approach. If it is going to work or not, that's a different story. But I mean, if it's going to uh, be accepted or not, that's a different story. But it will work for sure. So what we can do is we can, for every row, maintain a set, right? If we maintain a set for every row, then for the first row I can just maintain a set which only contains the corner values. Then for the second row I can maintain a set which consider all these values. For the third row, all these values. For the fourth row, all these values. For the fourth row we don't even require actually, because the last, for this example, the last row will be empty, right? The other section will be empty in that case, so that is invalid. But this is one approach that we can do. But just this set won't work. We need a set for this side as well, for this other section as well, that will maintain a row sum for the other section. Like for this, the last row will be maintaining these two values, and then the last second row will maintain these values, the last three will maintain these values, and so on and so forth. And then the same thing is extended to the column part as well. But this is a long I mean, it's a long approach, and it's going to give us TLE, because the fact that we are going to create a set and then pass this set to this set, and then create another set for the third row, and then pass that set to this set. So this passing itself is going to take O of m, and that's going to be n times, and then that's going to be for the four ways, that is this section, this section, this section, and this section. So it's going to TLE for sure, or it might even MLE, right? Because we are maintaining so many m cross n sections. But we need to know if that difference value, right, this difference value S2 minus S1, or S1 minus S2, whatever it is, the absolute difference value, is present in the one section which has a larger sum, in this case S2 section, right? How can I determine that in any other way? Well, I can maintain something like, for every value in the grid I can maintain a first and the last occurrence, right? First index and the last index. First index, last index, right? And then this first index and last index will be in four ways, right? So if I have this grid, if, I'm sorry for the bad handwriting, so this is the grid cell value, right? Then this cell value and this value are same. Suppose this value is also same, this value is also same, this value is also same. Then in this direction, the first and the last occurrence will be this and this, right? In this direction, the first and last occurrence will be this and this. In this direction, the first and last occurrence will be this, and then this and this, right? Actually, no. So in this direction it will be this and this, and in this direction will be the exact opposite. How it's going to help me? So if I maintain the first index and the last index, then I can see that this value, if it is present, and if it is present, then what's the index? This index is going to determine which section it is present in. If it is present in the section that I want it to be present, in that case I can consider this valid. If it is not, then I can consider this invalid, right? If it, what is the let me take an example. Suppose the value is 3. This is the 0th index row wise. This is the first index, second, third. Actually, the row is here. This is column wise. 1, 2, 3. Right. So if I'm going in this direction and I see that 3 appears in the 0th index as the first occurrence and the third index in the as the last occurrence. Now I see that this is the section that we are talking about and it has a value like 16. This has a value like 13, right? So this has a larger value. I see that 16 minus 13 is going to be 3. 3 is something that is present and the first index that it is present in is an index that is present in the first section. So I'm good, right? If it was something like 3 comma 4, 3 comma 3, right? If this was the case, then if it is, even if it is present, then I can know that it is present in the other section and not the first section. So I can't consider this a valid case and I'll move forward to the next row sum. So this is the way that we are going to create it and do it. It can be overwhelming and there are few very good edge cases that I am still yet to discuss. And that case is when we have a single row or a single column or a single row. In this case, if I can divide it in a vertical way, I can't do it in a horizontal way, but I can do it in a vertical way. Sorry, in a horizontal way, not the vertical way. So here, I can't just check the value, right? The lookup value that I get, the difference value. I can't just check the difference value if it is present in the other section or the below section. Even if it is present, then I need to first check what is the index of this value, right? It can't be a index that is in the middle. It has to be a border index, right? It can't be something like this. This is wrong. So it has to be a border value, and same goes for this section, and same goes for the row section. So it has to be this or this, and if we are checking for the other section, it has to be this and this, right? So either it has to be 0 or I, or it has to be I plus 1, and whatever this is row we are talking about, so n minus 1, right? So these are the border values. We need to have this edge case for both row and column. So let's code this up. Let's also create a steps. I won't go into too much detail in the steps. I just need few things. The row for the first partition problem like we did, the row and column is needed. So the row and column is needed. Create. Now the first occurrence and the last occurrence needs to be maintained. What data structure I'm going to maintain it in? Well, a map of integer to a pair of integer comma integer can be a data structure that we can choose, right? So create unordered map of integer comma pair of for row and row other section, right? Let me call it row section and row other section. Similarly, for the column section and column other section. Now iterate through the grid and populate the above structures, by the way, have default values for a value which is not yet present as int max comma int min. Why? Because straightforward, right? If I don't have this, then it's going to be by default 0 comma 0, and 0 comma 0 is something that can be our answer, so it shouldn't hamper our I should have a value that shouldn't hamper our answer. So I'm going to have int max and int min as the default values, and same goes for the column section and column other section. Populate the above structures, data structures, and lastly iterate through row sum or row array, maintain row prefix sum, and check if it is valid or not. I'm just being abstract here. There's a lot of things we need to do here, but we have to do it in the code and not here. So valid or not, repeat for column array, repeat step 5, and lastly return false. So let's code this up. So I have a m grid dot size. Let me copy few things here. These things are needed, right? So let me get this. All right, so we are almost good. So we need the 4 data structures for row section, row other section, column other section. By the way, there might be more ways to do this problem. This was more intuitive to me, but there are other ways, might be other ways to do this problem which might be simpler. So row section and similarly row other section and column section and column other section. Alright, so now if row section dot find grid of I and j is something that is not present, right? If it is not present, then row section grid of I and j needs to have default values int max and int min, right? And I have to do this for all the other section. So row other section, row other section, row other section, a lot of copy pasting. Let's be careful here. Column section, column section, column section, column other section, column other section, column other section, right? So we are good. Now I can just safely keep updating the indexes. So let's do it for 1 and then we'll copy this. So row section, but this needs to be updated very carefully, but we'll update this first. So row section of grid of I j is going to have two things, the first index and the last index, right? The first index will be the min value of grid of the min value of row section dot first, right? So min of section of grid of ij dot first comma I, and the same thing for the other index, but this time it's second and this time it's max, right? But the problem is I don't want to add this uh, yeah, I don't want to add this grid of ij to row section if it's a value that lies somewhere here. If it's a value that lies somewhere here, then I don't want that value, correct? Uh, Let me check one thing. Hmm, if this corner values are needed and the middle values needs to be avoided, then yeah, I guess we can't. So my bad. So what we have to do is here we have to avoid these values. We don't want these values, correct? We want just this value and this value. And the same goes true for this one and this one and this one. We'll extend that idea, but we'll do this for this particular section first. So here the row section of grid of ij needs to have only this and this and not these. So what I can do is, this is I. So when I is equal to 0 and j, that is the column, is not equal to 0 and j is not equal to uh, what is this? This is column, right? So column is n minus 1, n minus 1. So if this this condition represents what? These three values, correct? If this condition is not true, then I am considering these two values, correct? And these two values I'm going to add this to the row section. So what I can do is I can have a if condition here, which will be basically the fact that I is equal to 0 and j is not equal to 0 and j is not equal to n minus 1. The not of this is something that we want in the row section, right? And if it is I equal to 1 or 2, in that case this always is going to be true. So it's always going to be added here in the other section, in the row section. So now the same goes true for this. We will update now. So this is for row other section, which is from the back side. The things are going to be exactly same, but the only thing that will differ is I is now equal to m minus 1, because that's the back side of row, and this will still remain same. This will change completely. So column section, column section, column section. This will be j is now equal to 0 and I should not be equal to 0 and I should not be equal to m minus 1. Now I can just copy this down and I can say that j for the column other section, things can be confusing here, so I'll urge you to go through this and then understand. So j is equal to n minus 1 and this is going to remain same, and the only thing that's going to change is now we have j as the index, right? So we are good. So now what we can do is we can iterate. We are at step 4, actually 5. We have to iterate for the horizontal cut. So the horizontal cut, so for that I need a row sum, the prefix row sum. I am going to iterate this iteration. For every iteration I'll maintain a row sum plus equal to row of I. I'll check what's the other section sum, right? So other section sum is going to be sum minus row sum, right? That's my other section sum, and I need the difference. So this difference is going to be absolute difference. Absolute difference is what I need. Uh, yeah, absolute difference, row sum minus other section. Now if this difference is always going to be positive, so I have to check it against row sum and other section sum. So if the other section is higher, right? Other section sum is higher, or you know what? Let me check for the equality first. So if row sum is equal to other section sum, that means if this is the case, then I can safely return true. Else, if other section sum is higher, that means row sum is smaller. In this case, I need to check for this difference value to see if it is present in the other section or not, right? So if for the horizontal cut for the row, I'm checking the other section, so it's row other section where I need to check row other section dot find lookup, or diff value is what I'm checking. So if it is not, if it is present, in that case I can uh, check for the index. Now what is the index going to be that I want it to be, right? So I want the max value of this row other section, that is the second position. Second position is where I'm storing the max occurrence, right? So the max index of this value is something that is greater than equal to I plus 1, right? So my other section is defined by what? The partition. The partition is where I, we are here, we have this other section, this is 0, this is I. So I is basically the point where I am considering that point to be part of the first section. So I plus 1 is going to be the other section starting point. So my I want the value to lie, to have a index that's going to be greater than equal to I plus 1, right? So basically we are checking row other section of grid of ij dot second is greater than equal to I plus 1, right? If that is true, the last thing I need to check, I can return true here by the way, but before that I need to check the fact that if the, so I'm checking this, right? So what if the column so we are checking so yeah, what if the column is 1? In this case, I want the, so basically I'm saying that if the column is just 1, oh my bad, my bad. So I should have taken this example. So we are cutting horizontally, right? So we are cutting like this. So if column is 1, in this case, this is m minus 1, this is 0, this is I. So in this case, if n is equal to 1, that means column is 1, right? In that case, the row or the section, or I mean the diff value should be present either this point or this point and nothing else. So I can say that check for single column case where I'm going to check if n is equal to 1 and row other section of grid or actually diff, my bad, this should be diff, not grid of ij, right? So we are checking this value to be present or not. So if this value, the second position index, if it is not equal to m minus 1, and if it is not equal to uh, I plus 1, right? So I'm checking for the other section. If it is not equal to this, this and this, in that case, I can return false, right? And same goes for the other part where the row section is larger. That means I'm going to check the exact same thing. So it's going to be row section, right? Row section, row section. This time it's going to be the first point that we are checking, and if it's the first point that we are checking, then I want it to be smaller than equal to I, right? So that I can consider that at least one value lies in the first section. So again, the single column case needs to be checked. Here it needs to be row section. The first value will be checked to see if it is not equal to 0, and if it is not equal to I, then I can return false, right? So I'll copy this. I will do the exact same thing for vertical section. Vertical cut will be uh, exact same, just that we have to change few things. This will be column, this will be column sum, this will stay other section, this will be column sum, this will be column sum, this will be column, the one thing that will change here is now it is greater than equal to j plus 1. Actually I'm considering I only, so it should be I plus 1, my bad. So it is I plus 1, this is also good. This needs to be n minus 1 now, and this needs to be m is equal to 1 now, because we are checking for this case, right? So this is what we are checking. So we're checking if it is a single row, that means m minus 1, m is equal to 1. So if m is equal to 1 and then if it is not equal to n minus 1 and I plus 1, similarly here it will be column section. This will be column section. The things are exactly same. This is row case. This is row case. This is all good. Actually, this is not good. This is column section, column section, column section, column section. This is also row section, right? Yeah, so I think we are good, but there's definitely going to break at some point. Let's see if this works or not. By the way, I'm doing a lot of this should be true. This should be true, not false, and this should be false. Now let's see. Okay, something is not right. Let's see if the copy pasting was correct or not. So we're checking for the column section. That's good. This case is also good. This case also seems to be okay. Should be greater than equal to. This is also good. Other section is greater than column sum. So I'm basically checking if the other section is greater or smaller. That's okay. My bad, this should be J, not I. Let's see now. Okay, things are still bad. If it's equal, only then we return true. Not just equal, but equal to equal to. Let's see now. Okay, let's see. We're good. Let's submit this. Yeah, this is good. Time complexity wise, this will be O of m cross n. Right, this will be O of m. This will be O of n, and the space will be. Let's see. There can be, in worst case, all the values will be unique. So it's going to be O of m cross n 4 times 4 O of m cross n. That's going to be O of m cross n, and then m and n. So technically O of m cross n is going to be the space, right? And time as well, m cross n. So this is the two problems that I wanted to discuss. Thanks.